Major funding for NOVA is provided by the following. The David H. Koch Fund for Science, supporting NOVA and promoting public understanding of science. And by the Corporation for Public Broadcasting. And by contributions to your PBS station from viewers like you. Thank you. And Millicent Bell, through the Millicent and Eugene Bell Foundation. Major funding for Earth from Space is provided by the Kendeda Fund, furthering the values that contribute to a healthy.
Our best hope for answers may come from above. Orbiting over our heads are 120 satellites, keeping watch from space. Most operate at altitudes ranging from a few hundred miles above the surface of the planet to as high as 25,000 miles. Each one of these Earth-observing satellites reveals a different piece of the puzzle. Each carries an array of exquisitely sensitive detectors designed to reveal what would otherwise be hidden from our view.
The satellites are absolutely amazing because not only can we see the visible things from space, but also we can see things that aren't visible to the human eye. So satellites are enabling us to turn what are invisible processes into visible things we can see and then understand.
To see how our world works, in this program we have taken information provided by satellites, combined it with computer models, and rendered the results in these scientifically accurate graphics. With the invisible now revealed, we can see Earth as an endlessly changing system. These images will show in great detail how sunlight, moisture, land, and atmosphere interact in unexpected ways, with seemingly local events often triggered by forces far away in space and time. And with these new insights, for the first time, scientists can begin to understand the intimate relationship between the planet and all the living things it supports.
It's really the thrill, because it matters so much, of piecing together the story of what the Earth is doing, how it's changing, why it's changing, and how ultimately that affects humans.
The first piece of the puzzle is in understanding the massive influence the Sun, from 93 million miles away, has on our planet.
The world is continuously bathed in a flow of energy from the sun, and that warms the Earth. Everything that you can see that lives and breathes and moves on the Earth is pushed by the sun.
Now, an electronic eye in space can measure the impact of the sun's energy all around the Earth. One of NASA's newest satellites, named for a meteorologist, Polar Orbiting Suomi, launched in 2011, provides the view. The spacecraft is the size of a small school bus. It orbits 500 miles up, circling the planet 14 times a day. On board, it carries 5 separate sensors that enable it to see things invisible to human eyes. The light that we can see is confined to a narrow band of electromagnetic radiation, just a tiny portion of what the satellite can pick up. Electromagnetic radiation spans a spectrum that goes far beyond the familiar colors of the rainbow.
If you were to consider the full spectrum to be a line that stretched from New York City to Los Angeles, the piece that our eyes could see would be about the size of a dime. There is so much other information out there available to us, and that's in large part what these satellites do.
One of this satellite's key instruments is called CERES, an acronym for Clouds and Earth's Radiant Energy System. It detects a broad range of the spectrum, including the very short and very long wavelengths of light in the ultraviolet and infrared that we can't see. This is a Ceres I view of the planet. Anything that emits heat gives off infrared radiation, so the Ceres data shows the Earth in shades of heat, accurate to a fraction of a degree. It reveals how the planet as a whole reacts to sunlight, both absorbing and reflecting the radiation coming from our local star. At the poles, the sun strikes at an oblique angle, and what little light there is gets reflected back out to space by the ice and clouds. These are the primary reasons why the poles remain cool. At the equator, it's a very different story. Not only does the planet receive more direct sunlight here, the lack of ice means that less of the sun's energy is reflected back into space. And at the equator, the sun's concentrated energy fuels a heat engine that can trigger weather events around the world. Perhaps the best place to see the impact of the sun's heat is an area in the Atlantic just north of the equator and west of Africa, the coastal waters of the Cape Verde Islands. Here, the sea provides a living. The local fishermen keep a careful eye on the weather. They know that storms can bring a good catch. Turbulent weather stirs up nutrients from the deep, attracting great shoals of fish. It's the hottest time of the year, and the sun beats down relentlessly. By late afternoon, the huge inflow of heat energy has led to the buildup of large cloud formations. Sometimes these formations develop into massive storms. It's a process that satellites are revealing in fine detail. Circling above the fishermen is a NASA satellite called Aqua, Latin for water. It orbits the poles. One of its key tasks is to monitor the complex interaction between sunlight and water.
Aqua satellite is one of NASA's flagship satellites. Its primary function is to study the hydrologic cycle on Earth. Vapor in the atmosphere, liquid ocean, the temperature of that ocean, and the ice.
One of Aqua's instruments looks down at the sea around Cape Verde, again in infrared, sensing heat. Highlighted here in yellow, over 1 million square miles of ocean reaches a critical temperature, 80 degrees. At this temperature, the sea is evaporating fast, producing an invisible gas, water vapor.
By looking at the infrared, the Aqua satellite is able to measure the amount of water vapor evaporating from the surface of the ocean.
Aqua shows that this area is producing millions of tons of water vapor every hour. Based on that data, it's possible to create an image of what the vapor might look like if these fishermen could actually see it in the air around them. Water vapor is much lighter than air, and vast columns rise upward directly from the surface of the sea. The water vapor carries with it heat, the energy of the sun.
Well, water vapor is like invisible energy. It's like molecules escaping the ocean, taking heat energy with them, and they're like little mobile solar collectors that are zipping around the atmosphere.
Half a mile up, as the air cools, the water vapor condenses back into liquid water, tiny droplets that form vast clouds. The vapor releases the sun's energy, the heat it received earlier. The result is a storm.
Molecules condense in the atmosphere and become liquid again. And when that happens, that heat is given off into the atmosphere and it warms the atmosphere, and that's the heat that powers storm systems.
In the worst storms, the heat captured by the water vapor is equivalent to up to 200 times the global production of electricity at any given moment. The process of evaporation results in something we don't need special instruments to see. The rising heat drives the clouds up to 10 miles high. As the clouds rise upward, the Earth's rotation causes them to spin. The thunderclouds merge into a vast vortex. This is the birth of a hurricane. It is 2005, the busiest hurricane season on record. On August 27th, a meteorological satellite is tracking a Category 3 hurricane that started in the Bahamas. Its name is Hurricane Katrina. Throughout the region, there is one question on everyone's mind. Will the hurricane hit land, or will it blow itself out? The answer may come from a NASA satellite called TRMM, the Tropical Rainfall Measuring Mission. TRMM is equipped with a radar and imager that operate in the microwave range of the spectrum. These are higher in energy and shorter in wavelength than other radio waves. The instruments bounce microwaves off raindrops in the clouds, allowing scientists to build a three-dimensional model of the internal structure of a hurricane.
We can actually look at microwave energy, which is generated within the clouds and coming from the ocean surface. It's almost as if the clouds are now invisible to us. We can see right through them, like taking a CAT scan to look inside those clouds.
This satellite is a powerful tool. And now, its sensors reveal something ominous. Huge vertical columns of warm water vapor burst up from near the center of the storm. Almost like hurricanes within hurricanes, these climbing vortices deliver added infusions of energy into the heart of the storm, fueling its growth even more. These new sources of energy are called hot towers.
If they occur in the right place at the right time near the very center of the system, they could be like a giant spark plug that gets that whole engine running at very, very high speed.
The hot towers draw more and more water vapor off the ocean. This triggers a feedback loop that leads to a runaway reaction. In just 24 hours, Hurricane Katrina grows into a Category 5 monster. All this violence is a direct result of the power of the sun on the ocean. Ferocious winds blow for 2 days straight, reaching 175 miles an hour, twisting steel like paper and ripping apart homes and buildings. Over 3 trillion gallons of rain a day, and a massive tidal surge from the Gulf of Mexico combine to inundate whole areas of the Gulf Coast. Katrina leaves its mark across 90,000 square miles. Over 1 million people are displaced. Katrina becomes the standard by which future hurricanes will be assessed. But even this extreme hurricane is just a tiny brushstroke in a much bigger picture. A picture of how the sun drives water around the entire planet, with radically different effects in different places, all under the watchful gaze of our eyes in space. Take just a single day in July. In New York, commuters swelter in 95-degree heat. Searing winds pump hot air into the region from the south, creating oppressive, humid conditions. 7,000 miles away, in Mumbai, India, commuters here struggle to cope with torrential rain. The deluge comes so fast that the streets are flooded in hours. Meanwhile, in Chile, the desert of the Atacama is almost totally dry. There are places here where rainfall has never been recorded. Such diverse environments thousands of miles apart appear totally unrelated. But by pulling back for a wider view, we can see that they are in fact intimately connected. Orbiting 22,000 miles from Earth's surface is a chain of 5 weather-tracking spacecraft, including this one, NASA's GOES-East. GOES is an acronym for Geostationary Operational Environmental Satellite. Each moves in a fixed position relative to the Earth, called a geostationary orbit. They always look down on the same parts of the planet. The combined data from these 5 satellites gives scientists a unique perspective on the Earth.
By having several of them located at different positions around the equator, we're able to get a view of the whole Earth 24 hours a day.
By observing the entire Earth, these satellites reveal how energy moves throughout the globe, beginning with the impact of the sun on water. The process is the same everywhere, but the outcome will be very different in different places. Converted from the numerical data, these 5 circles graphically depict what the satellites actually sense. They reveal the total picture of water vapor produced on Earth in a single frame. Seen here in fast forward, 1 second is equal to a day. It shows how water vapor produced at the equator continuously transports the sun's energy towards the poles. Local landscapes and topography affect the vapor's impact, with results unique to each region. In India, at the end of July, the warm water vapor is drawn from over the ocean by the difference in temperature between land and sea. Rising to high altitude, the vapor cools over the land and condenses back into water. We call the result the Asian monsoon. Nearly 1 trillion tons of rain falls out of the sky, transforming parched land into fertile plains. The monsoon eventually moves to the east, reaching China, where it floods the paddies that are ideal for growing rice. This process helps provide food for 3 billion people, almost half the world's population. Meanwhile, on the other side of the world in South America, westbound winds drive water vapor across the high peaks of the Andes. The altitude strips the air of its moisture, which falls as snow on the mountains, creating, on the far side in central Chile, the arid desert of the Atacama. That same July day, in the eastern United States, hot, moist air surges north, straight from the Gulf of Mexico. With no natural barrier in the way, more than 100 million Americans, from Memphis to New York, swelter in the summer heat. This graphic, based on information provided by satellites, depicts the interaction between the atmosphere and the oceans as they connect in a global pattern of circulation that results in our local weather.
The satellite data shows that it's all one interconnected system, but that in different parts of the world, different processes are happening. We can see the monsoons and their effect. We can see the effect on deserts in a different part of the world. And that together shows us how water vapor is connecting with life on Earth.
But this vast cycle of sunlight, water, and land is just one pattern among many on this planet we call home. A cycle with even greater consequences for the long-term climate involves extreme cold. To see how that works, we have to turn the Earth upside down and look at it from below. solar current together form an impenetrable barrier around Antarctica, isolating it from the rest of the planet and depriving it of warmth. That is why the whole region remains exceptionally cold all year round.
What's incredible about what the satellites tell us is that the movement of air, and actually the movement of ocean current, around the perimeter of Antarctica isolates the continent from the rest of the world.
So why is this relentless cold so important to the planet, way beyond Antarctica? The answer lies in a remarkable property of water: what happens when it freezes. The Aqua satellite reveals the start of the process. It sweeps the surface with its microwave scanner, looking through the clouds to detect the distinct signature of ice.
The microwave instruments on the satellite enable us to see through the clouds to the sea ice around Antarctica throughout the year. What's particularly incredible about that is we're able to take measurements of the sea ice in places where, as scientists, as humans, we can't even go.
This satellite gives us an accurate picture of the extent of sea ice around Antarctica over the course of a year. Seen here in summer, Antarctica is nearly 1.5 times the size of the United States, covered in ice. But in winter, it grows even more. Over 5.5 million square miles of ice form around the continent. It grows to the size of all of Africa. This vast ice formation has a profound effect on life across the planet. How can its impact extend so far? One of the best places to understand the power of ice is the huge bay along the northwestern coast of Antarctica, the Weddell Sea. Here, a constant gale blows and cools the seawater to freezing temperatures. Once the upper layer of ocean falls below 29 degrees Fahrenheit, a critical threshold is crossed. The surface of the ocean begins to freeze. At a microscopic level, tiny crystals start to grow, knitting themselves together. As the crystals bond, they expel salt into the water. The salt forms brine that drips down long, narrow tubes and holes in the ice as it forms. The brine is denser than regular seawater, and it sinks downwards. As winter's grip tightens, the formation of ice speeds up and spreads. Soon, large slicks appear on the surface and thicken into a solid mass. What started as a microscopic process can soon be seen from space. Each year, more than 200 billion tons of ice form in the Weddell Sea alone, releasing tens of trillions of tons of dense brine into the ocean. The fate of all this brine is a mystery. The crucial question is, where does it all go? A satellite called JASON, jointly operated by NASA and the French Space Agency, is providing new answers. JASON bounces radar signals off the surface of the ocean to measure its height. The instrument also reveals the shape of the sea floor far below.
We can make very accurate maps of submarine bathymetry. But we don't do that directly. We do that by measuring the surface of the sea from space very, very accurately and over time.
JASON's radar is so precise that it can detect minute changes in the level of the sea surface produced by the peaks and valleys of the terrain below. The data makes it possible to map the ocean floor.
You have a satellite that's up there 500 miles up in space, and it's returning an accuracy of a little less than ½ an inch. What that means is, I stuck this instrument in Washington, D.C., say, and I'm looking at a crowd of people in Boston, and I can tell you whether or not their toes are over the curb or not. That's what the satellite is doing.
The satellite data allows scientists to make a three-dimensional map of the ocean floor beneath the Weddell Sea. It reveals a vast chasm, 2 miles deep, off Antarctica's continental shelf. As the brine descends into the ocean, it eventually falls over this precipice. Other sensors attached to the sea floor track the flow of the brine as it sinks.
What we're really excited about is that we're able to take that data that shows us what the bottom of the ocean looks like and combine it with data from sensors under the water. And that enables us to look at the dense water and where it goes.
Combining data from satellites and undersea instruments, scientists can reconstruct what is happening hidden beneath the ice. What they learn is astounding. $1 trillion gallons of salty brine plunge down through the Weddell Sea every hour, a torrent equivalent to the volume of 500 Niagara Falls. The brine spreads out towards the edge of the Antarctic continental shelf and then falls into the chasm revealed by JASON. A vast submarine waterfall plummets downward. The cold, dense brine falls slowly, silently, into the abyss, 2 miles down to the ocean floor below. It will not resurface for hundreds of years. What happens to the brine next is still being investigated. But computer models combined with satellite data are helping scientists to figure out where it goes. This animation shows the undersea current in action. The purple area is the brine. The outflow from Antarctica drives the salty water towards the equator, along the sea floor.
All the water in the bottom of every ocean around the globe has its start within 6 miles of the Antarctic continent. It creates the coldest, densest water that's on the planet.
The cold, salty liquid becomes part of a worldwide circulation system, stirring and cooling all the world's oceans. Leaving Antarctica, it has embarked on a journey that could take 1,000 years to complete. As it migrates towards the equator, the cold bottom current mixes with fresher and warmer water and slowly rises. It then joins other ocean currents and eventually returns south, where it cools once more. Finally returning to Antarctica, the seawater freezes and releases its salt again, completing the cycle. It's an endless loop that is critical to the whole planet.
The importance of dense water in Antarctica is that it really forms the basis of global ocean circulation. The temperature and the salt combine to cause sinking and rising in different parts, which sets up this conveyor belt, this interaction of all of the ocean water.
In the Arctic, frigid winter winds show us how this happens. Over time, we can see in fine detail how the Earth's crust is constantly moving. This is the surface of the crater atop Mount St. Helens in Washington State. Animation reveals how it swells over the course of 3 weeks, driven by a surge of molten magma beneath the crater.
Now, satellites can actually see the crustal plates moving now. We can see bulges and dips where the magma is moving around underneath the crust.
This animation shows the swelling of Mount Etna in Italy as magma accumulates beneath it over 9 years. When the volcano erupts, the land sinks back.
So we're getting a picture now of what the world looks like under the crust and how that affects the other dynamic processes of the so-called solid Earth.
Every day, dozens of volcanoes around the world are erupting, while 4,000 earthquakes shake the ground. Our Earth is dynamic, constantly ejecting gases and magma from its depths, and some of this activity has a vital impact on life. The secret to understanding how lies deep beneath the ocean surface. Here, a crucial chemical reaction takes place between molten rock and deep ocean water. The JASON satellite's sea surface mapping radar reveals a chain of active volcanoes 1.5 miles down at the bottom of the Pacific Ocean. This is where that critical interaction between molten rock and freezing water takes place. This footage was taken with a remotely operated submarine, also called JASON. Lava and superheated gases spill out of cracks in the ocean floor, known as hydrothermal vents. JASON reveals what happens when cold ocean water penetrates into the cracks. A magma chamber below heats the water to up to 750 degrees Fahrenheit. In the pressure cooker environment inside the cracks, the dense, salty water actually dissolves the solid rock. Complex chemical reactions take place, producing minerals containing sulfur and iron. These are nutrients that living organisms need to survive. The seawater, now loaded with minerals from inside the Earth, streams out of the hydrothermal vents. These nutrients feed a thriving ecosystem that includes shrimp and exotic creatures like tube worms. The deep ocean currents carry the leftover nutrients away. Over thousands of years, they circulate through the oceans, ultimately rising to the surface and contributing to an amazing explosion of life. And we can see this activity with NASA's Aqua satellite, which is equipped with instruments that observe the Earth in many wavelengths of the electromagnetic spectrum. One tool is called MODIS.
MODIS is pretty much the crown jewel of the Aqua satellite. It's an enormous scanner, so it basically covers the whole world every day.
MODIS scans the ocean in the infrared and the visible portions of the spectrum. It can detect extremely subtle changes in the temperature and color of the water.
So what we have in space is an instrument that looks at very, very small parts of the spectrum. And we measure how much light comes back in each part of the spectrum.
Looking down at the west coast of South America, MODIS detects an upwelling of cold water 150 miles west of Peru. Then it detects a particular shade of green. This identifies the source as chlorophyll, a sign of plant life. It's clear that the satellite has spotted a massive bloom of tiny organisms called phytoplankton. Just below the surface, these phytoplankton are absorbing the rich soup of minerals that have come from the deep ocean. And with light from the sun and carbon from the carbon dioxide in the air, they multiply by the billions. As MODIS shows, the plankton multiply so quickly that in just 24 hours, trillions of anchovies and sardines feast on the tiny organisms. They, in turn, attract larger predators to one of the densest concentrations of marine life anywhere. Sharks converge, and even birds, flying above, dive down to join the feast. And up above, humans are here too, taking advantage of one of the world's most productive fishing grounds. The satellite data reveals similar upwellings all around the world, delivering nutrients, seen here in pink, into the surface waters. Each upwelling triggers a plankton bloom.
Phytoplankton provide that key link between this energy out here, the raw materials that this planet holds, and the food engine that allows life to flourish.
These vast green ribbons of plankton can cover as much as a fifth of the world's ocean surfaces. About 45 billion tons of biomass every year. The plankton are one link in a chain of life that begins deep beneath the seafloor.
The most important plant life on this planet are these microscopic little green plants that float in the ocean.
Plankton may be key to life, but they themselves don't live long. MODIS shows how, in just 72 hours, a bloom can rapidly weaken and fade. All the plankton that have not been eaten die and sink into the abyss. They take their precious minerals with them all the way back to the ocean floor. Here they will remain for millennia, a thick carpeting of tiny carcasses half a mile deep. Some of the minerals may ultimately be recycled. Some may emerge through hydrothermal vents again, millions of years from now. But some plankton, through yet another extraordinary chain of events, will deliver their precious cargo of nutrients not just to life in the ocean, but also to life on land. Half a world away from the coast of Peru, where plankton bloom, lies the Sahara Desert in North Africa. The Sahara is enormous. It makes up a tenth of the African continent. It's one of the driest and dustiest places on Earth. Surprisingly, the remains of ancient plankton are here, hidden in this arid landscape. It is May, the hottest month of all. Camel herders travel through one of the most exposed regions of the Sahara, the Bodele Depression. 6,000 years ago, this was covered by the world's largest freshwater lake. The floor of the lake is covered with the ancient remains of plankton, called diatomite, laid down in a much earlier age, when an ocean covered the region. With its eye on the Earth from 400 miles above, NASA's Landsat 7 is one of the latest generation of satellites studying the composition of rocks that make up our planet. It sweeps the Bodele, producing these high-resolution pictures in multiple wavelengths of visible light. The white expanse is the diatomite on the bed of the lake.
The size of the lake is over 1,000 kilometers long and 600 kilometers wide. But with a satellite image, we can see the whole extent.
Thank
nature and our own. Unlike volcanoes, the motion of ocean currents, or the oxygen produced by forests and plankton blooms, we make conscious decisions about what we do. And here, satellites are crucial once more. The information they provide can help us meet the challenges of the future.
The real power of satellite observations is they represent objective truth. They tell us about what the world actually is doing, not what we would like it to be doing, not what we might fear it to be doing, but what it's actually doing. And it's that that allows us to see change, real change, for what it is.
Satellites are telling us that the oceans are slowly warming. In the past 30 years, the average temperature of the ocean's surface has risen by ½ a degree. Models suggest this extra heat could be increasing the intensity of hurricanes and violent storms all around the world. Satellite data shows that in Antarctica, ice shelves that took many thousands of years to form are collapsing year after year. And in the Arctic, sea ice is diminishing at an alarming rate. Many factors play a part in these dramatic changes, but most scientists agree that human activity, through our release of greenhouse gases, is the main driving force. All around the globe, satellites are recording change, but there's a problem. Just as we are able to capture and measure these changes, many of the current fleet of satellites are coming to the end of their lives. Satellites need fuel to stay in their orbits. When their time is up, they must either use the last of their fuel to boost themselves far away from the Earth or descend and burn up on re-entry. It's predicted that the number of NASA's Earth-observing satellite systems will go from 20 down to fewer than 10 within the next decade. The constant stream of information from these vital instruments in space will fade. If we fail to replace these satellites, we could lose our ability to track the web of connections that is fundamental to life.
The complex interactions would be absolutely invisible to us without a larger view of the Earth. It's the consistency and the amount of data that they provide that allows us to understand the processes that are going on in the Earth that are important to maintaining life as we know it.
Little more than half a century after the birth of satellite technology, we're still only beginning to realize its possibilities. Our planet harbors mysteries beneath its white clouds, blue oceans, and verdant landscapes. And they can only be solved with the help of these eyes in the sky, looking down at Earth from space.
Major funding for NOVA is provided by the David H. Koch Fund for Science, supporting NOVA and promoting public understanding of science. And by the Corporation for Public Broadcasting, and by contributions to your PBS station from viewers like you. Thank you. And Millicent Bell, through the Millicent and Eugene Bell Foundation. Major funding for Earth from Space is provided by the Kendeda Fund, furthering the values that contribute to a healthy planet.